Hi everyone, and welcome to the Introduction to R. Um, I know that a lot of you are already familiar with R, which means that a lot of this will be review and you can probably breeze through most of it. The whole point behind this little vignette is to just give a basic introduction to people that maybe haven't used R or they're really not very comfortable with how they've used R in the past. And it's really just to kind of set up the tool that we're going to use for the rest of the semester when we actually start getting into some statistics. Um, so why R? R is a free statistical programming language, and free is always good, and it's especially good when you consider that there's a whole globe of scientists and data scientists and the like. And it's kind of nice that everybody has free access to it, so that way it's not something that only certain kind of privileged institutions that can afford the very expensive types of statistical software. Also, if you do a quick, if you go through a recent issue of almost any kind of biological science journal, you'll see that the vast majority of the papers in those journals are actually using the R statistical computing environment. So it's really become one of the, if not the most popular statistical softwares out there. So it's a good tool set to learn. There's a lot that can be learned in R, and obviously this is not a class on R. We're learning how to use the tool. And so the purpose behind today is just to give the very basics in the introduction to R, and then as we start doing more complicated things in R, we will we'll introduce those concepts as we go along. And so R is free, it's widely used. It also has a fantastic development community, meaning that there are lots and lots of people out there who have really clever ideas on how to deal with various types of data, and maybe they invent new methods or they come up with more efficient ways to do methods, or maybe they're just nice and they figure out ways to automate things that normally would take you a long time to do. And all of those libraries or packages are also freely available for you to install in your R environment. So that makes it really nice because there is this really great user community. And the user community is also great because if you have trouble with anything, if there's anything in particular that you are kind of unsure of, or maybe you have a unique problem that we didn't even cover in the class, you could do a search for that and you will find hundreds of different responses to that same question just by simply doing a Google search. Like, how do I do this in R? And you will get lots of hits on that. So the large user community makes it really nice, and it tends to not be opaque, meaning that it tends to be easy to follow. Oftentimes people provide examples. So it's kind of a nice kind of community of people that use this that are really trying to help other people actually learn how to use R as opposed to just simply plugging and chugging. So historically, when I first started doing this class, I actually used a GUI interface, GUI, graphical user interface, which was a program called JMP, or JUMP for short, which is developed by the fine people at SAS. And I stopped doing that for a couple of reasons. One is that it's very it's very limited in how flexible you can be and how creative you can be once you understand a little bit more about statistics. Maybe you want to be a little bit more creative than those particular writers or authors of that software thought you should be. But the main reason why I have liked the transition to R is that, as we'll see, R is a language where it's all scripts. And so we're going to actually be writing a little bit of computer code when we're doing our analysis. And the advantage of that is that anybody in the world, if they have your data, they can look at exactly what you did with the analysis and they can recreate your results perfectly. And so it provides some nice transparency and repeatability to your analysis. And that sounds like, well, why couldn't I do that with a GUI interface? It can get really tricky with a GUI interface because, you're pulling down windows and you're saying you want to do this, and then you're hitting this button, and then you're this little pull down tab, and you'll get the results, but you won't necessarily have a record of all the little tiny options that you did along the way to get your data, or to get the results of your analysis. Whereas in R, all of your scripts are there, so you can follow it from the raw data to your final conclusion, or the results of your analyses. And so that makes it nice. Now that said, it is a scripting language, and there is a little bit of kind of quasi-programming involved. And as such, I'm very empathetic that there is also a learning curve to that. And there's really no way around it. There is going to be a little bit of a learning curve, especially if you are new to R. And so again, the point of today is just to give you a very kind of basic introduction to it. As you play with R more and more, you'll get better and more comfortable with it. And yeah. Okay, so first thing we want to do is we want to figure out how to get R onto our computer. And so I'm going to go ahead and I'm going to make myself small. There I am, small. And then here, all I did was a Google search for R. And all I typed in was capital R, and sure enough, the first thing that pops up is this R project for statistical computing. So I can go ahead and I will hit that, and now it'll load up that. And then I just go here to download R. It's going to ask me for a mirror. And that's just, so because R is free, there are repositories around the world that are maintained that that basically have the program there for you to freely download. Whenever you're confronted with this question about what mirror you might want to use, I always pick the cloud one. The cloud one will simply find the one that is best for your purposes. And so now we're here, and we want to download and install R. So if you have a Mac, you select here on download R for the Mac OS, and then follow the instructions. It's pretty straightforward. Same thing for Windows. So let's go here. Let's pretend I'm on a Mac, because I am on a Mac, and there you can see here's the latest release, 4.0.2. All I have to do is download that package and install it, and then I now have R on my computer. Likewise, if I had a Windows machine, I would just go to Base, because you'll notice this is what you want to install R for the first time. So you just go to Base, install R, everything will be fine. And then if you are on a Linux machine, you're on a Linux machine. You don't need me to tell you what to do, because you're already very comfortable with dealing with command line. Okay, so after we've installed R, I want to think a little bit about the fact that of what R is. So again, R is just the most basic of programs, really. Let me see if I can make that a little bit bigger. I can't. So here I'm on a Mac, so I opened up Terminal, which puts me into the Unix environment. And if I were to just type in the capital letter R, there's R. I now have R. It is loaded, 4.0.1, so I don't have the newest edition. You can see this version is called Arbor Day. Little piece of trivia, they always have a different cute name for each version of R. I think one of my favorites was Stupid Kite Eating Tree or something like that. Apparently they're all references to Peanuts comics. Don't know why, but you know, I don't know. I guess if you spend your whole life writing a statistical code, you might as well at least amuse yourself with Peanuts comics. Right, and so this is base R. So I'm here, and I can go ahead and I can type in here, and this is a very kind of primitive way of interacting with R, and this is probably not the way that any of you are going to interact with R. So I'm going to go ahead and I'm going to terminate that. So after you download R, let's take a look at what R looks like. Now it looks kind of the same, but you can see it's a little bit gooey-er, right? There's at least little tabs up here that I can select. There's also a menu up top, and so on and so forth. And so if I were to go ahead and click on that, now what I have is I have what's called a text editing window or a script window, and over here I have my console window. And again, the console window is where you're actually talking to R, but what we're going to want to do throughout this class, and really as a good habit whenever you play with R, you're never going to want to interact directly with R. You're going to want to interact with it via a script window. And so I can pull up this script window, and I'll just type the number 7 for no reason, but why not? And so I can keep track of, okay, I put the number 7 there, so I could cut and paste that over to R, make that a little bit bigger for everyone. So I put the number 7 in there, and R has confirmed for me that indeed I put the number 7 in there. Not terribly interesting yet, but what I wanted to point out is that I did this over here in the script window, and then this is how I'm interacting with R. Okay, so this is what I sometimes refer to as the quasi-GUI R, because it's almost GUI-ish, but it's not quite 100% GUI. I'm going to go ahead and I'm going to quit. I'm not going to save my number 7. I'm not going to save that. How we are going to be interacting with R, or at least how I'm going to be interacting with R, and I highly encourage you, strongly encourage you to interact with R, is a program called RStudio. And so again, after you've installed R on your computer and you've gone through this, if you were to do a Google search for RStudio, you'll see that first thing that pops up is download RStudio. So you're going to go ahead and you're going to download RStudio. What RStudio is it's a shell, meaning that it talks to R, but it gives you a lot of kind of convenient options, and it's an easier way to keep everything in the same place. I confess for a couple of years I was a Luddite and refused to use RStudio because I was really happy with that quasi-GUI R, but I've come around, especially after teaching this class and realizing that everybody else was using RStudio, so I probably should too. And so I'll go ahead now and I'll open up RStudio. And here we have RStudio. Now the first time you open up RStudio, it will look slightly different from this. Let me get myself out of here a little bit. It'll look slightly different from this. I believe that the console window is usually at the bottom, and I think the script window is usually at the top on the left-hand side. I've reorganized it this way just because for teaching purposes, it was easier than having some of the stuff at the top and some of the stuff at the bottom of the screen to have them side by side. All that stuff is easily adjustable in the preferences for RStudio. So you can change around the order of, you know, where your various windows are, so on and so forth. But let's look and see what these windows are. So first we have our console window. So again, I can put the number 7 in there, and then R is telling me, indeed, I did put the letter or the number 7 in there. And then over here is the important bit. This is our script window. This is where we're going to actually write all of our scripts. And we're going to always want to write our scripts in a script window instead of directly through terminal, because once you do something in terminal, it's there, but R has forgotten it. And so it's just in the buffer, but it's not very easy to rerun that particular script because you have to kind of cut and paste. It's much easier to write all your scripts over here, and that way when you save it and you're finished for the end of the day, you can easily open it up on the next day and all of your scripts are there, and you don't have to kind of reinvent any kind of wheels after you've already invented them once. And so so that's pretty much it. And then there's some other stuff here that we'll kind of stumble upon and talk about. Environment can be helpful. It tells you what objects, which we'll talk about in a second, are in your environment. And then down here we'll have a help window, and then we can also look at plots or files that are local and so on and so forth. And so that's the first step of this little vignette. How was that for fast and simple? If you don't have R on your computer, I would hit pause on this little video, and then go ahead, install R, install RStudio on your computer, and then come on back to the video. So we'll take a really quick pause, and I'm going to make that beeping stop. Alrighty, welcome back. Hopefully you have installed R and you've installed RStudio on your computer. When you open it up, you can always go underneath File, and you can say I want to write a new R script, and then it will show up here. Here it is for me. It's untitled number 4. So now I have a blank R script. Again, this is the place where we're going to type our code, and then we're going to send our code over here to the console, which is actually where we're talking to R. Now, as I mentioned before, yours might look a little different. I believe the default is to have the script window in the upper left-hand corner, and the console window in the lower left-hand corner, and some other stuff over here in the right-hand corner. This is just how I like to set it up, and I found that, at least back when I used to be in front of real people, lecturing with the computer screen behind me, it was easier for people to read the whole screen, and that way they weren't, stuck. If you were sitting in the back of the class, it was kind of hard to see stuff that was at the bottom of the window. And now I've just gotten used to setting it up this way, and so that's how I roll. You can change all that if you go to Preferences, Pane Layout, that's how you can say. So here I'm saying console in the upper left, source in the upper right, and then I have all this other stuff on the bottom. You can also change the appearance if you want. You could, make it look all these different kinds of colors and all this neat stuff. Xcode, ooh, extreme. All right, I'm gonna stick with text default, although Xcode looks nice, but I'll stick with text default. And say, okay, apply. And so those are just kind of different, those are all kind of aesthetic adjustments that you can make on it. At the end of the day, RStudio is simply a shell that's running over R. So, okay, the first, probably most important thing and I'm just going to be going through that intro to R script that I put on the canvas. The first, probably most important thing, or one of the most important things to do, is to annotate your code. Annotating your code means that you're simply making comments or notes to yourself or to other people so that you can explain exactly how you did something and why you did something. So it's basically just, it's kind of like a post-it note. You're just able to kind of keep track and keep notes for yourself. And it can be extremely helpful, especially when you're learning new statistical methods, so that you can remind yourself why you did something at each step. And we annotate our code using the pound symbol or the hashtag. Somebody gave me this and I can actually use it as a prop. Look at that. There's a hashtag. Comment. And this is what we do to do a comment in R, which means that anything that we type after that hashtag is entirely ignored by R. So if I were to say hashtag comment in R, and if I were to take that and put that over into the console window and execute it, R does absolutely nothing because R doesn't care. It's totally ignored me. But it'll come in really handy when you start writing computer scripts and you have lots of different steps. Maybe you did a transformation and you want to explain why you did that transformation, or you've excluded certain data points and you might want to explain why you've done that. So that way when you come back to it in the future, you kind of know where your headspace was at the moment when you were actually writing the computer code. And certainly on our homeworks, we're going to ask you to annotate your code. It's always better to over-annotate than under-annotate, so that way anybody can follow along the steps that you're doing. Okay, so annotation of code, really important. The old hashtag symbol. It does more than just, it's more than just trolling people on Twitter. It's actually a way to annotate your code, so we will remember to do that. So R, again, is a statistical programming language, which means that at some level it must operate as a simple calculator. And the operators that we use for calculators are the familiar operators that we use in anything else. So 1 plus 1, if I were to copy and paste that over into R, it gives me the number 2, which is the correct answer, I hope. For the next 5 minutes, if that, ignore this little bracketed thing that says 1. That'll make sense in just a second. So for now, let's just ignore that. The answer here is 2. Okay, 1 plus 1 equals 2. And likewise, I could say 1 minus 1, which is going to do what? It's going to equal 0, hopefully, and it does. Okay, so there we go. We've added and subtracted using R. We call it a day. With this whole cutting and pasting thing, it can be very cumbersome, and by habit, most people don't even do it anymore. If you are on a line of code and you hit Command and Return from within the text editing window, it'll automatically cut and paste it over into R. And so that's just, a really kind of handy thing to do when you're writing code, so you're not always cutting and pasting, because that can become rather cumbersome. And it's just Command Return, And I believe that's also true on Windows machines. If it's not, let us know. It's control return them, but I think it's command return. And again, with the annotation, I could annotate that 1 minus 1, and I could say this subtracts 1 from 1. And then if I go ahead and cut and paste that over, notice I did it that time, and that's how I'm going to do things from now on. I'm just going to automatically cut and paste it over here. Again, there's my comment. This subtracts 1 from 1, and R has ignored that. If I had just put that in there, R is going to give me an error. It's like unexpected symbol, and this subtracts. It doesn't know what to do with it, so it's just giving me a really vague error message, which isn't making a lot of sense. And that's because we didn't comment it out. Okay, and then obviously we have our other operators. So if you wanted to do division, 1 divided by 2, it is the slash. I always get confused as to whether or not that's called a forward slash or a backward slash, but let's just call it the slash. 1 divided by 2, cut and paste that over there, equals 0.5. Okay, that works. And then multiplication, 1 times 2, we use the asterisk for multiplication, and there we have it. Okay, and so we have simple mathematical operators. If we were to do 1 divided by 0, I show that one because you will get this thing that's called inf, and that inf is saying that it is infinite, which is going to restrict the kind of arithmetic you can do on it, because unless you're doing calculus or limits, it's difficult to think about how to deal with infinity. So just be aware, if that ever pops up, you probably did a division by 0, and you probably didn't want to do a division by 0. Okay, so that's kind of the basic, okay, good. Jim just had you download a really large program that can add and subtract. Pretty handy since, we all have smartphones probably. Okay, so let's get on to what R is about. So R is a what's called an object-oriented language. It likes to deal with objects, and as long as you give it the appropriate objects, oftentimes it'll know what to do with that object. A little piece of trivia, R is also what is called an interpreted language, meaning that when we're running code, the computer is actually reading our code one line at a time. This is different for those of you that have had experience with other types of languages like C++, which is a compiled language. It's a little different because in a compiled language, you have to turn it into machine code before you can even run it. R, you don't have to do that. R is that nice and kind of interpreted language, which makes things a lot easier, especially when you're a beginner at programming. I guess it comes at the cost of interpreted languages tend to be very slow. In the context of our class, and R class, I guess. In the context of our class, the reduction in speed really won't matter. I don't think you'll notice that, that took 1/100th of a second, but if I had done that in C, it would have taken 1/1,000,000th of a second. You're not going to really notice it in R, but just to be kind of aware of some of the terminology that might get thrown around with that. So it's an object-oriented language, which means R wants to deal with objects, and that's how we're going to keep track of everything. Because right now we've done this arithmetic over here, but R has no memory of it. It did it, and it's done with it. But we might want to save a particular value, and because we might want to manipulate that value in the future, and that's what comes down to creating what are called objects. And so if I were to just type in the letter A, and then I were to put that over into the console, I will get an error saying object A not found. And that's because we haven't defined what object A is yet. And so to create an object, let's say that we wanted to assign, what did I do up here? I assigned the value of 2 to A. The symbology that we use is this less than and then a hyphen symbol. And then I'm going to give it the value of 2. Okay? And so this is something that at first you're like, okay, why am I doing this little silly symbol here? Well, there's a couple of reasons why you're doing that silly symbol. One is that it's convention in R. I guess that's one reason to do it. The history of it, as I mentioned before, R is based upon S, and S was developed, I believe, once again, I'm pretty sure it was developed at Bell Laboratories. They actually had a button on their keyboards that was an arrow. And so what this is supposed to look like is it's supposed to look like an arrow. And how you would describe this to people is you would say A gets 2. And so you're saying that A is going to get the value of 2. And so once I do that, now if I were to type in just the letter A, the value 2 comes up. And so that's pretty neat, which means I could do something now with that. What if I wanted to say A plus 6? A plus 6 equals 8. Why? Because the object A has the value of 2, and 2 plus 6 equals 8. Because it's an arrow, you could switch the order of this. You could say that 2 hyphen A. That will do the exact same thing. If I look at the value of A, it's 2. I only show this because very rarely, if you're doing a Google search for a help on something, or if you're looking in some, I don't know, I've come across it in some weird places where people will do it in that direction. Don't ever do it in that direction. Pretend I never told you that. I just wanted you to be aware that it's a thing. Generally, you put the object and then you say gets and then the value of that object. Now you can, as of like 10 or 11, maybe 12 years ago, you could, if you wanted to, use the equal sign. So I could say that A equals 2. And now if I look at the value for A, it again equals 2. That is generally considered bad form in R, mainly because, as we'll see shortly, we will actually use the equal sign for what are called arguments within functions. And when it comes to the readability of the code, it's much easier to have a different symbol for the gets symbology when you're assigning a value to an object versus the equal sign, which is generally used in arguments. So it's not wrong to use an equal sign. That is something that actually does appear a bit when you're looking for help online. I would encourage you to avoid it just because it's bad practice, and I certainly will always be using the get symbol because I'm all about best practices. I guess I can also mention that the spacing here doesn't really matter. So I could say A gets 2, and that's going to be the exact same thing here as it was up here. But the less than sign and the hyphen, they have to be together. There cannot be a space in between there. Okay, so we know how to assign a value to an object, and then once we have that object, obviously, we can do some very basic arithmetic on that object or mathematical operations on that object. So again, I could say A plus, what did I say back here? I said A plus 6 equals 8. And then you can also, let's create an additional object. So I'm going to say that B is going to get 4. So now I have 2 objects in my working environment. And let me move my little bald head here out of the way. And over here in this RStudio window, you can see in the environment, I have 2 different values. I have a value for A, and that value is 2, and I have a value for B, and that value is 4. And so this is just a handy way of knowing what objects are in your particular workspace. You could also clear out the workspace by simply hitting this little broom here. That'll remove everything from your working space. And so this idea that this phrase that I'm using called working space, it is what is currently in your R environment. And so if I was to restart R, A and B would not be in my environment, and I would have to redefine what A is and what B is. And this is just a handy way to find out what is in your particular working space. Okay. And so now we have two objects. We have A and B. So we could do any kind of, A times B is 8, right? Because what is A? A is equal to 2. B is what? B is equal to 4. 2 times 4 is 8. And then likewise, I guess the only other mathematical operation that I haven't mentioned yet is to do exponents. So if I wanted to say 2 to the 4th power, so I could say A to the B, right? So A to the bth power, that's going to be the same as 2 to the 4th power, because A is equal to 2 and B is equal to 4. But we could always change, if we wanted to, the value of A. Let's say we change it to 7. Now we can go A to the B, and we get 2,401. Okay, so now we've overwritten the old object value, and so this is something to always be aware of, that whenever you use that gets symbology there, you are going to overwrite what your previous value is for that object. So just be aware of that. I'm going to go back and I'm going to make this 2. And I'm often pretty bad about putting spaces with the get symbol. I'm trying to get better, especially for this purpose, because it's considered, best practices to have the space, but I tend to jumble things up. So, okay, what else do we need to know about objects? Objects, they don't have to just be one word, right? And so I could say Jim's favorite number is going to get 13. And that sounds weird, but 13 has always been a really lucky number for me. And so now there's this object called Jim's favorite number. Okay. Objects are case sensitive, meaning that even though I've created an object called A, if we look down here in the lower left, if I were to type in capital A, there is an error. Object capital A is not found. So R is case sensitive. It can be a mixture of lowercase and uppercase. It can have numbers in it, but it cannot start with a number. So I could say Jim, oops, not there, I won't. I'll do it in my editing window, like I said. Do as I say, I will do as I say. If I were to say Jim second favorite number, and I don't really have a second favorite number, I will say 7, because that's another prime number. I'll stick with that. And so I was able to put the number 2 there. I cannot start an object with a number, but objects can also include other symbols. In particular, common ones that people use are a period or an underscore. So, I might put a period in between each of these, just because it'll make it an easier way to read it. When coming up with names for objects, it's always, it's kind of important good practices to make sure that you're not using a function name as an object name. And that's kind of tricky when you're first starting out, because you don't really know that many function names yet. But for example, there is a function called mean, which, as you might guess, calculates the mean of something. And you would not want to create an object called mean just because it will be harder to follow your code, because there'll also be a function called that. R is at least smart now. Back in the old days, if you had assigned an object called mean, it would actually overwrite the function that actually calculated the mean, and then you would have lost, for that R session, your ability to use that function to call the mean. So just as a kind of as a general rule of thumb, avoid the common function names. And we'll see those. Again, I appreciate the learning curve. We'll get there. Fret not. Okay. And so we have our object A and B, and I don't even remember what they were. A is that, B is 4. Okay, A is 2, B is 4. And so also with thinking about arithmetic, we're going to R follows the convention for the order of operations, so it'll do things in parentheses first, and then it will do multiplication, division, and then it does addition, subtraction after that. And so if I were to say A divided by 1 plus B, that's going to give me a different answer than A divided by 1 plus B, right? Because here in this top one, the first thing it's doing is it's adding 1 to the value 4, because our object B has the value 4. And so it's going to be 5 in the denominator, and it's going to be 2 divided by 5, as opposed to here, it's going to do order of operations. So first it's going to do 2 divided by 1, and then it's going to add to that 4. And so be aware of that when you're manipulating data in R, that we have to keep track of our order of operations, which is pretty much the same thing that, that you have to do in like Excel, for example, or anything. Okay, so R not only has these operations like plus and minuses, we also, there are a number of built-in functions into the base R package. And I'm going to, again, as we go through the course, we'll introduce new functions. So the purpose behind today is just to simply understand how to use functions. And so the first function that we're starting with here is called sqrt, which will calculate the square root. So one nice thing about official R packages that are both built into base R as well as ones that we will at some point be installing in our library is if you put a question mark before the name of a function, sqrt, a help file will pop up here, and it'll tell you what it does. And so here we have, it's giving us one for ABS, which is the absolute value of something, but then here is sqrt, which computes the square root of x. And it'll tell you how to use that function. And so it's going to be sqrt of x, which means that it is expecting a value there. And that's the value that we will give it. And here, the next line is telling you what the arguments are. And the arguments are what? X. It's telling you what x is. It's a numeric or a complex vector or array. We'll get to complex vectors and array in just a second. But basically, it has to be a number. It has to be numeric. And so if I wanted to, say, figure out the square root of b, let's remind ourselves what b is. B is 4. So if I wanted to know the square root, I would say x is equal to b. Okay, so again, this is where we are using equal signs because it's in an argument. So in this case, we're calling up the square root function, and x is going to equal b. And if I run that, it gives me 2. Now there is a shortcut. In the beginning, as you're playing with these, it's probably a good idea to kind of be verbose, write out the whole argument. But because there's only, in this case, there's only one argument, as long as you put your arguments in there at the order at which they're asked for in the function, you don't have to explicitly say x equals. So in this case, if I were to just say sqrt of b, that's going to give me the square root of b. Okay. And so let's think about other common things that you might come across when you're playing with this. If I were to take the square root of negative b, I get a warning message. It's not an error message, it's a warning message. But I get a warning message saying that nans were produced, N-A-N-S. And N-A-N stands for not a number. And that's because, as you I'm sure you'll recall, we have imaginary numbers, the little I, that we might deal with if we're taking the square root of a negative number. Now, if you do a Google search for imaginary numbers in R, you will find tons of resources as to how you can do imaginary numbers in R. For our purposes, it doesn't matter, so we're not gonna go over it. I just wanted to do this to point out that that's what that NaN means. NaN means not a number. Okay. And so again, if we go back to this, ABS does the absolute value. Well, if I did the absolute value of negative b, it's 4. So that makes sense, right? The absolute value of negative 4 is going to be 4. Okay, let's get on to a slightly more complicated function that has multiple arguments in it. And I'm going to pull up log. So I'm going to say question mark log. And we can look at the help file for that. And here we have 2 different arguments for log. Okay? We have x, and then we have base. And the default, when R is showing you in these help files, when it's completing the argument, where it says base equals exp1, well, the exp1, the exponent of, or exponentiating 1, that is Euler's number, right? That is the natural, the base of natural log. So what the log function will do is it'll give us the natural log of our number. So if I were to say I want to take the log of b, it's going to give me 1.386294. Okay. If I were to take, we can look at the second function here, log 10. Log 10 takes the base 10 logarithm. Okay. And so if I were to say log 10 of b is 0.60206. Okay. I could also use this log function to do the same thing by just changing that base argument. So I could say, so give me the exact same answer, log, log of b base equals 10. Well, that gives me log base 10. So really, you can do all the kind of logs that you want or need to do using the log function just by changing that argument. And again, if I wanted to be more explicit, I could say x equals b and base equals 10. And the one thing that is important is, for being explicit, is that order will not matter if you are happy, or order will not matter if you're explicit with your arguments. So in other words, if I were to type log base equals 10, x equals b, it's going to give me the same answer. If I didn't type the arguments in there, I'm going to get a different answer, because what it's doing is it's taking the log of 10 at base 4. And that's not probably what we want. And so that's why it's a good idea often to be explicit with all of your arguments. And again, as you get more comfortable with it, you'll figure out which ones you feel comfortable skipping. Usually we want the natural log of something because it seems to work just fine. So typing that is perfectly fine. Now, once we've calculated the log of b, that's all we've done. We have not saved that value. And if we wanted to do something else with that value, then we would want to assign it to an object. So I'm going to create an object that I will call log b. Okay? There is no function called log b, and well, there actually is. I don't even know what the heck that is. Oh, there is one, log b. Well, that's neat. I'm going to put log.b. Never heard of that before. What am I thinking? Okay. So I'm going to say log.b is going to get log b. And now I've created an object called log b, which is 1.386294, which means that now I could use the exp function. I could exponentiate that, exp log.b, to get back to my original value. Okay? And so that's why if we know, and we generally will want to use, whenever we've done any kind of calculation on something, we're probably doing it because we want that calculation. And so oftentimes, just as by default, you'll just find yourself assigning everything to an object, and then it's just a matter of keeping track of your objects. Okay, so that's the basics of creating a very simple object. This is an object that only had one value. In a lot of statistical languages, that might be referred to as a scalar. And I suppose it is a scalar in R, but it's really what's considered to be a vector of a length of 1. So it could be a whole list of numbers, but it's not. It's just one number, or a whole series of numbers. Got to be really careful about that. Okay, so objects can also be characters. So here I'm creating one called M that's going to just simply say hello. And so now I have this object that if I typed in that object, it would tell me hello. And then likewise for N, I can say goodbye. So now I also have an object called goodbye. And so if we were to look here at our global environment, get me out of there. If we were to look here at our global environment, it's telling me what the values of hello is and what the values of goodbye is. We could also use a built-in function called str, which I often do just because it gives sometimes a little bit more information. But if I were to say, what is the structure of A? It's telling me that it's a number and it has the value of 2. If I was to do the structure of M, it would tell me that it's a character and that the value is hello. Okay? And I know all this stuff might seem a little arcane at first, but it'll make a lot more sense once we actually start playing with real data and with complex data sets. You're going to want to keep track of what your data actually are. Another way that you can look at what's in your environment, if you're like me and you just are not used to looking at this little global environment thing, is if you were to just type in ls parentheses, it'll tell me the name of all of my objects in my current working environment. So these are all the objects I have created in this particular working environment. Okay. And then if I were to do, I guess, if I were to say ls.str, now it's giving me not only all of the things, but it's also telling me what they are. Okay, so Jim's favorite number, it's a number and it's the value of 7. M is a character and it's hello, so on and so forth. So, okay. And so now let's think about a few other things here. Let's think about logicals. And logical statements are things like less than or greater than, and what they will return to you in the R environment is a true or a false. So if I want to say A is less than B, nope, I didn't mean to do that. Didn't mean to do that. And it's dangerous. A is supposed to be 2. If I were to say A is less than B, as I said, I'm so used to hitting that less than hyphen sign that I didn't mean to do that. But okay, so A is less than B. It's giving me true. I can say is A less than or equal to B. That's also true because again, A is 2 and B is 4. If I were to say A is greater than B, again, the spaces don't matter. It's going to give me a false. I could likewise say is it greater than or equal to B? False. And then so those are pretty obvious what they're doing. And then there's 2 other operators that that come in handy that maybe aren't as intuitively straightforward. One is to ask whether or not something is equal to something else. Now remember I said that you could use the equal symbol to assign an object, and you don't want to do that because you might want to ask, is A equal to B? You don't want to turn A into B. So what you would do is you would say A, and then you do double equal signs B. Okay? And so that's false. 2 is not equal to 4, which means that A is not equal to B. So when I'm asking is A equal to B, the answer is false. when I started, I reminded myself that it was the double equal sign, and when we're doing this in class, if we ever use this symbology, I always say to myself, super duper equal to, because it's got two equal signs. So you're really getting at whether it's super duper equal to it. And then the other logical that's worth knowing is not equal to. And that is done with an exclamation point and then an equal sign. And so that's saying it's not equal to, and I run that, and I get a true. So again, I get these trues, and I get these falses. And these will come in handy, as we'll see in just a few moments. Okay. So that brings us to the next part. So at this point, we've created objects that have one value associated with them. And I mentioned that in some languages, that might be referred to as a scalar. For us, it is really a vector that has a length of 1, meaning that there's only one item in that vector. But objects can be vectors, and all a vector means is a series of values. So you can have more than one value associated with an object. And so I'm going to create a new object. I'm going to cut and paste it right from the handout that I gave you. Okay, so here I'm creating an object called A, capital A now. And I'm going to give it these values, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. To create an object that is a vector, notice that I had to put this little lowercase c in front of it. Okay, so this is one thing that you're just going to have to get used to in R. When you're dealing with a vector, you have to put a little c in front of it. And c is a function, and it is a function that's going to combine together a bunch of different values. And so here it's saying I want A to be combined or concatenated all of these values into a vector. So if I go ahead and I do that, and you can see here is our vector of values, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this brings us to what is this little thing that's over here in brackets? All that is R trying to help you out to let you know where you're at in your vector. So let's say that I had a really smaller window, and then I'll go ahead and I'll look at A. Now what you notice is now I have two different numbers in brackets. And so what these numbers in brackets are simply telling you is which number of that vector is that particular value. So here it starts at 3, right? And this is telling you that, okay, you're starting at 1. So the first value in that vector is 3, which means that the second value must be 4, so on and so forth. But then once we get to the next row, because they're not truly rows, right? It's one long vector, but here we've shrunk the window down. It's telling you that this 11 here is the 9th value in that vector. And so that's just R trying to be helpful, letting you know where you're at in your vector. And obviously with something as short as this, not going to matter all that much, but when you're dealing with a vector that's a couple of thousand long, it can become pretty handy to know where you're at across all those values. So now we've solved the mystery of what that thing in brackets is all about. So when I was talking about the advantages of R earlier, one of the other advantages of R is that it can deal with vectors really well, meaning that we can put mathematical assignments to a vector and it'll cover the entire vector. So I can say things like A plus 2. A plus 2. What A plus 2 will do is it'll add 2 to everything in that vector. And sure enough, 3 plus 2 is 5, 4 plus 2 is 6, 5 plus 2 is 7, so on and so forth. And so we can add values across that vector, but once we've done that, A is still A. We haven't changed the value of A. So if we wanted to keep or save a vector that had these values, which is simply A plus 2, we would have to create a new vector. So let's call it Z. Z is going to equal A plus 2. Now we have this additional vector called Z, which actually has those values of interest. And we'll be doing stuff like this quite a bit later in the class, like when we transform variable, or when we transform data, or we center data, we'll probably want to create a new object that is the log transformed data, or the z transformed data, or whatever it might be. Don't worry about those details, we'll get to them. But you can do any of the standard kind of operators that we talked about that you could do with single valued objects, scalars or vectors of length of 1. So I could do, I could create z again, but this time I want it to be a divided by 10, and then here's the values of a divided by 10. I could multiply it, why not? A times 5 is that. What is z? It's giving me that. And then I could square all of those terms if I wanted to as well. And so using the caret again, it's going to square them. And now z is that. And I could take it to any power I wanted to. I want to take it to the 7th. I want a big number. I want big numbers. There's a bunch of big numbers because now it's to the 7th. Okay? So we can do any of the normal types of things that we had played around with before. We can also put a vector into many of the functions that we've already talked about. So if I want to do the square root of a, here's all the values for the square root of a. Let's remind ourselves that's what a is. So the square root of 3 is 1.732. The square root of 4 is 2, obviously, and so on and so forth. The ones I could do off the top of my head were the square root of 3 and the square root of the square root of 4 and the square root of 3. Be pretty impressive if I memorized that, which I've never done. I don't plan on doing it. And so you can do that. Likewise, we could take the log of a, and that's going to give us the natural log of a, and for each of those values. Okay, and so you can imagine that very rarely are we going to be dealing with objects that have only a single value. Rather, we're going to be dealing with objects that have more than one value, which is data, right? We can't really do much analysis on a datum, but we can do analysis on data. So, okay, and so I'm going to create a second vector here. And this vector is going to be called b, okay? And I'm going to just give it these values. And so now I have a vector called a, and I have a vector called b. I can add those two vectors together. And if I said a plus b is 100. That's 100 plus 3, which is 103. That's going to be 90 plus 4. That's going to be 80 plus 5, so on and so forth. So we can add two vectors together very simply. Now, if we had a shorter vector, I'm going to create another vector called c. And I'm going to just give it the value of 15 and 25 and 35. And now if I were to say a plus c, it's going to add those two vectors together, but they're different lengths, right? A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 long. And c is only 3 long. So when I'm adding these two vectors together, what's going to happen is the shorter of the two is going to be recycled. So notice, first of all, R gave us a warning message. It's not an error message, it's a warning message. And it sounds serious because it's in red, but a lot of times that's R just trying to let you know, saying, hey, just wanted to give you the idea here that some of these vectors are different lengths from one another. And as a consequence, what happens is when you have a vector that's shorter than the other, is that those values are going to get recycled. And so if we go back to A, and we go to C, and then let's go back to A plus C, ignore our warning message. So 18 here is 3 plus 15. 29 is 4 plus 25. 40 is 5 plus 35. Okay, so those are the first three values. But now that we get to the fourth value for A, which is 6, we're recycling C. So it goes back to 15. So 6 plus 15 is 21. And so the warning messages can be nice because oftentimes you don't want necessarily to recycle values. It usually means that you've done an oops, and you got to figure out where that oops is and why your vectors are of different lengths. But thinking about the fact that when we created those simple objects with one value, the way to think about that is that it's a vector that has the length of 1. And so when we said a plus 1, right, essentially we're recycling that value. We're taking the first value of a and we're going to add 1 to it. And then we're going to take the second value of a, but this only has one value in it, so it's getting recycled and it's applying it to everything across the entire vector. And so you can do all the kinds of math that you might like to do on a scalar or on a simple single valued object. You can do all of that on a vector. And vectors, they can be pretty long. And again, just to here's the values of this. So one thing you can do, I'm going to create a vector called z, and I am going to simply say 1 colon 100. And what that's going to do is it's going to tell R to count from 1 to 100 by increments of 1. And so if I were to do that, I can look at z, and again, here are my brackets here, right? The first value is 1. The 12th value is 12. The 23rd value is 23, so on and so forth. And these little bracketed numbers that R is giving you to try to help you out is, you could imagine, let's take a scenario where we got 9 to, I don't know that. Okay, and now we look at Z. Well, now R is making it easy for us because we know that 185 is the 177th value in that vector. And that can end up being handy because oftentimes we're interested in extracting particular values from a vector. And that brings us to the next thing, which is called indexing. So I'm going to go ahead and I'm going to hit A. And here we have again our vector that's called A. We should all feel good and warm and squishy about our vector A. And let's say we wanted to pull out just the first value. We do that by doing what is called indexing. And this little bracket here that R was kind enough to give you gives you a hint as to how we might do that. So if we wanted to call out the first value in that vector, all we need to do is type the name of the object, and then we use square brackets, and I want the first value. That's the first value. Likewise, if I wanted to get the first 4 values, I could say 1 colon 4. Because remember, if I do 1 colon 4, it's going to count from 1 to 4 by integers. And so this is my way of telling R I want the first 4 values of that vector, which is 3, 4, 5, and 6. 3, 4, 5, and 6. An alternative way that you could do the exact same thing is to put the vector in there explicitly. So we could create a new vector within there called, we could say lowercase c, because again, that's telling R that we're going to give it a series of values. And then I could say 1, 2, 3, 4. That's going to give me the exact same thing as saying 1 colon 4. The 1 colon 4 is just a handy little shortcut. And it can also be complex. So I guess the example that I gave you in the handout was, let's say that I wanted the first 4 values, and then I wanted the 6th value. So now going back and looking at our main object here. So the first through 4th value, 3 is the first, 4 is the second, 5 is the third, 6 is the 4th, and then 8 is the 6th value. And it's skipping over, or it's not extracting all the rest. Okay, so it's just a way that we can extract information from the vector, and we can also eliminate things from the vector. Let's say that I really don't want the number 4 in there. And I know that the 4 is the second value. So I could say, if I said minus 2, that's going to give me the vector A except for that second value. And so that's where the minus 2 comes out. Now notice, just because I hit that minus 2, it's still part of A. I haven't changed A at all. And that's because we didn't reassign it. Especially when you're beginning at R, if you're a beginner at R, if you did want to create a new vector where you have eliminated the second value, it's always better to create a new object that has that, because there is no undo in R. Once you do something and you overwrite an object or you change an object, there is no, Command Z or whatever it is to undo. And so, especially when you're beginning, it's really easy to get yourself into trouble if you were to do something like A is going to get A minus 2. Okay, so now A no longer has the number 4 in it, and it's gone. It is entirely gone from that object. And the only way that we can put it back into that object is to recreate that object, which can be a pain when you start doing complicated things. So just as basically as a good kind of standard practice, especially when you're beginning, is don't overwrite the names of your objects. Go ahead and have a filthy environment with lots and lots of objects in there. It's better to do that than it is to accidentally overwrite an object that you didn't mean to overwrite. Okay. So now that we have this object, and I have my old A back, I believe. Yep. Okay. Eliminate that. Oh, so if you ever do something like this where you're like, ooh, I never want to do that, but I don't want to delete it because I want to remind myself how to do what I never want to do, this is a good place to put our little friend, the hashtag. Because you'll notice A has not changed because all of these operations here have come after the hashtag. And you'll also notice in RStudio that it changes color when it's a comment. So. Okay, so a few more functions that we can think about now that we have a vector. We can calculate the mean, which I mentioned earlier. So the mean of A is what? Mean of A is 7.5. That's pretty neat. There's a few other commonly used ones that we can play with. Sum. That takes the sum of all those numbers. I can ask for the minimum value of all those numbers. 3. What is the maximum number of all those values? 12. Now obviously in this case here we're dealing with a really, really small object and it's ordered from lowest to highest. We wouldn't need to use minimum and maximum, but you could imagine if you had an object that was maybe 20,000 different values and you wanted to know what the minimum value was of all of those, that's when the min function could come in really handy. And then finally, a handy one is length. And it'll tell you the length of the vector. It is 10 long. Okay. I could sort it. So that's sometimes something that we're interested in doing. We could say sort A. And so now it's sorting it from lowest to highest. If we did question mark sort, we would see that one of the arguments is decreasing. The default, this is the default setting. That's why it's giving you a value after the equal sign. The default setting is false. And so if I wanted to say I want it to be true, I would say A, or I could say X equals A. It's going to do the same thing. Comma, and then I would say decreasing equals true, because the default is false. We've already seen that. Trues and falses are all capitals. Whenever that's an argument in a function, it's all capitals. And so I go ahead and I do that, and now it's doing a decreasing sort of that. Notice I have not changed A at all. If I wanted to have sorted, decreasing equals true, I could create another object if I wanted to called decreasing a or d dot a or whatever I wanted to call it. Where are we at? Oh yeah, so logicals we can apply to a vector and it'll apply it to everything on that vector. So if I were to say a greater than 9, I get a series of falses and trues. So one nice thing about R, and this will come in handy with your own data as well as with things in the class, is that it treats trues as 1s and falses as 0s. And so I could ask the question, you know, okay, how many values here are greater than 9? And I could do that since we know that a greater than 9 gives me all these falses and trues. I could ask for the sum of that. What's the sum of a greater than 9? And again, it's considering falses to be 0s and trues to be 1s. And so if I do that, there are 3 values in my vector that are greater than 9. And I could do, you know, all the other types of, how many are greater than or equal to 9? Well, there's 4 that are greater than or equal to 9, and so on and so forth. We can also use these trues and falses to pull out values of interest within a vector. So let's say I just wanted to look at all of the values that were, say, greater than 9. I could say a, and then I could put the logical statement right in there. A greater than 9. Those are the 3 values that are greater than 9 in my vector. And sure enough, here's my vector again, reminding ourselves. 10, 11, and 12 are indeed the only values in that vector that are greater than 9. This has the same function as, or serves the same purpose as using an actual function, and that function is which. And you could say which what? Which a's are greater than 9. And if I go ahead and I run that, it's telling me 8, 9, and 10. So those are not the actual values that are greater than 9, but what those are the indices for that vector that are greater than 9. So the 8th value is greater than 9, the 9th value is greater than 9, and the 10th value is greater than 9. The 8th value is 10, the 11th or the 9th value is 11, and the 10th value is 12. And so I could similarly call out those values by doing that. Okay? It's a different way to do the exact same thing. I actually like doing it this way just because it's more explicit and it's easier for other people to follow. Okay, and so finally, vectors can also be characters. And so I'm going to create a vector. Where did I create those hellos and goodbyes? Where was that? That was up here. M and N are hello and goodbye. So I'm going to go ahead and I'm going to create B. This is slightly different actually than the notes I gave you. In the notes I actually just redefined them, but here I'm going to just say B is going to get M and N. So now I got hello and goodbye. That served the exact same function as if I had done this. Hello, comma, goodbye. Hello and goodbye. And so vectors can be letters or can be characters, that's fine, but they can't be both. And so if I were to try to create something new called V, and I were to say that V is going to be hello and goodbye and 2. And if I were to run that, this has got to be in quotes, June. There you go. If I were to run that, I don't get any warning message or anything like that, but if I look at that object V, notice that 2 is in quotes. And 2 being in quotes is R's way of telling you that it is not considering that to be a number, it's considering that to be a character. So it's not recognizing it as the number 2. You can think of it as it's recognizing it as the letter 2. Okay. I need to drink some water because this is just lots of talking. I'm gonna take a break, and then we can come back probably with a new with in part two, and we'll wrap this up as quickly as possible, while hopefully trying to maintain some clarity. Okay. Welcome back to part two of the Intro to R. Again, I know that this is kind of long and dry, and but I figured it's better to go slow, introducing kind of the basics so that you feel comfortable playing with it, than to try to sum up everything in a matter of 15 minutes. Um, and again, if this is all review for you, feel free to just kind of skip through until something pops up that is potentially of interest. Right, and so where are we at here with the intro to R little notes that I've sent around? Oh, I wanted to point out how to remove stuff from your workspace. So, you can see we have all these objects in our global environment, and again, I can use that function called ls and just give it open parentheses, and I hit return, and it's telling me everything that is in my everything that's in my workspace. So those are all the objects that we've created. And so what I can do is I can remove all that by simply saying remove list equals ls. And now if I were to do ls, everything is gone, right? And over here, there's nothing in our environment. If I rerun, this is why it's good to save your script. So I could repopulate, I could rerun all of the R stuff that we've already done, and now my environment is once again populated with all those. And again, it's the same thing as over here. If I hit the broom button here, it will remove the objects from the workspace. And so if I do that, are you sure you want? It cannot be undone, because there is no undo in R. I can say yes. Now the environment is empty. ls, nothing, right? There's nothing there. It's just there's nothing. That's that character 0 means. Okay, so just wanted to point that out, because sometimes when you're playing around, your environment can start getting really crowded, and maybe for your own sanity, you don't want some things in there, and so you can always remove them from your workspace. Okay, so this brings us to the next kind of object. So up to this point, we've talked about vectors and how to index things out of vectors. Next, I want to talk about what I refer to as matrix-like objects. Actually, I'm not the only one in the universe that refers to them as matrix-like objects, and they are exactly as they sound. They sound like something that sounds like a matrix. So you can imagine that this is what data look like when you have an Excel spreadsheet all filled out. And as a simple example, we're starting out with, I'm going to create an object called eggs. Okay? And let's say that these are the total number of eggs observed from butterflies or mosquitoes or whatever it might be. Again, we've created that object. Here are the values in that object. And then let's say that we look at those eggs and we don't want to wait for them to hatch and do all this other stuff. So instead what we do is we just sacrifice the eggs and we genotype them to figure out whether or not we think that they are a female or whether or not they are a male. In this case, let's say mosquito. And so I can say male.offspring is going to get what? I'm going to just cut and paste it because that's the data that I gave you. Okay. And so now that's the male offspring for each of those different groups. So the first brood had 5 eggs, 3 of them were male offspring. Second brood had 2 eggs, 1 of them were males, so on and so forth. So again, we can use the vectors. We can do arithmetic on vectors, and so if we know which ones are genetically males, we can figure out how many of them were genetically female. So I'm going to say female.offspring, and then I will say female offspring is going to be what? It's going to be the total number of eggs minus the number that were indicated as being male mosquitoes. We like male mosquitoes, they don't bite. And so now we have this vector that describes the female offspring. okay? And so we can do the other types of, playings that we've done with vectors before. We could say, well, which ones of those, have a value of equal to 2, or which ones, were there more than 2 female offspring, and we could pull out what those values are just by doing the same kind of matrix kind of manipulations that we did in the previous little video here. So what I want to talk about is, what do we do when we want to put that into a matrix-like object? So it looks a little bit more like the data that we actually are used to dealing with. And so let's see here. We are going to say egg.data. We're going to create an object called egg.data. And what I'm going to do is I'm going to combine them by columns, which means that I'm going to have one column that's going to be the total number of eggs, one column that's the male offspring, one column that's the female offspring. And to do that, I use a function called cbind. And I'm going to cbind together what? I'll cbind together males, females, and then I'll also do total eggs. So now I have this object. And if we look at it down here, or up there, I guess, is where I'm looking at right now, you can see that it's numeric, and it's 1 through 10 and 1 to 3. And what that's telling me is that there are 10 columns, or 10 rows, rows 1 through 10, and there are 3 columns, columns 1 through 3. Okay, so if we were to look at that egg data, that's what it would look like. So now things are starting to look a little bit more like, oh, that's what data look like. I've seen that before, right? And so that's that. We could also have made egg data where we had 10 columns and only 3 rows by using a function called rbind. And so everything is the same as when I use cbind, but now I'm using rbind. And the way that you can think about what cbind and rbind mean, because especially cbind, that's something that we will use quite a bit, is that you are binding together a bunch of columns. That works for me. Or you are binding together a bunch of rows when in regards to rbind. So if I look at rbind, now you can see this is what my data looked like. And I can stretch this window out, and there we have it. Okay. Notice that the window is narrower. It wrapped, right? And again, this is R being friendly to us, telling us, well, starting here, that's the 8th column. That's the 9th column. That's the 10th column. And that's going to become handy because we might want to start selecting out those values. So first, let's go back, and I want to stick with the cbind way of putting my data together because this just looks better. And this is the general format that most data will be in, you know, when you input them into an Excel spreadsheet and then you read them into R. And so we can always get information about this. We can say dim, which will give us the dimensions. So if I said egg.data, it's saying it's 10 by 3. And so in general matrix math, when people talk about it, but in computers in general, usually you first start with the rows by columns. So it's not columns by rows, it's rows by columns. So this dim of the egg.dat is telling me that there are 10 rows and there are 3 columns. And so we can call out particular values from that by using the index, just like we did with a vector, except now we have more than one value to call out that. We need to tell R what row do we want, and we need to tell R what column do we want. So let's say hypothetically I wanted the value from the 3rd row, 2nd column. And so we know off the bat that that value is actually 2. So you might say, Jim, why the heck would I ever do that? I can look at it and see that it's 2. And that's totally true, but it becomes more cumbersome when you have 1,000 rows of data and 40 columns. Then it can start being difficult to kind of keep track. But we can call out that by just simply saying egg data. And then again, it's always rows by columns. So what do we want? We want the 3rd row and we want the 2nd column. 2. That's the value that's there. Okay. Female offspring is the name of the second column. That's the name of the second column. And the value of the 10th, or I'm sorry, of the third row in the second column is indeed 2. Here's the third row, and here's the second column. And so there is the number 2. We can also look at the values. We can extract columns or rows out of this matrix-like object and basically have it return a vector. So if I wanted only the second column, I could type in egg.data. And then if I leave a blank there and type in 2, what that's telling R is that I want all rows, only column 2. So when you see that blank, that's telling you the extent of that dimension of the matrix-like object. So if I were to do that, now that's giving me all the values for female offspring. And then if for some reason I only wanted to extract the values, say, of this 10th individual or this 10th female that laid these eggs, I could say egg.data. I want the 10th row, but I want all columns. And if I do that, that's the 10th row, all columns. And so this can be a handy way not to only extract things, but also just to kind of check on your data. And as you start troubleshooting, when we have real data, we're always trying to troubleshoot. We can find things easier and kind of surf around in this. When you are reading in a really large data set, one thing that can be handy is this function called head. And what head will do is it'll just show you, by default, it shows you the first 6 rows, but it shows you all the columns. And again, this can be really handy if you have an absolutely enormous data matrix. Okay. Last thing is we have this egg data. I'm saying last thing because I'm looking up at the notes here. Let's say that we wanted to remove the eggs column because, well, the eggs column, that information is included here, so maybe we don't want this for some kind of an analysis we're doing. We could remove egg. We could redefine egg data, and I'm going to say that egg data is going to get egg.data. And what am I going to do? I want it to include all the rows, but I want to remove the third column. And so just like with a vector where we could remove particular values, that -3 is going to say entirely remove the third column. So again, this is a great example as do as I say, not as I do. I'm overwriting egg data right now, right? I'm going to redefine what egg data is. It's going to get what egg data currently is minus the third column. And so now I no longer have total offspring at all. And that is potentially a problem because maybe I wanted that in retrospect and I've removed it and there is no undo in R. And so there are 2 different ways that we could cook back up that data, right? So I could create a new object that I'll just call total eggs. And I could just say that it's going to be egg.data, all rows column 1, that's going to be the males, plus egg.data, all rows column 2. So now I've created a vector that has what the total number of eggs were. The other way that I can do the exact same thing, and this function does come in handy, especially when we're not just simply adding things together, is there's a function called apply. Okay, and let's go ahead and let's do question mark for apply. And apply is a way to apply functions over the margins of a matrix-like object. Here we're calling it an array, which we'll get to in just a second. And there are 3 different arguments that are of importance. X is the array, which includes a matrix. We'll get to that in a second. But that means that we could go ahead and we could say capital X is going to equal, and it's going to equal what? It's going to equal egg.data. That's the name of our object. And I'll go ahead and I'll put spaces here to make it nice. Good conventions. The next thing is the margin. And the margin is telling R what direction to do this particular function. And so if you remember, it's always rows by columns. So margin 1 is to do something by rows, and margin 2 would be to do something by columns. And so if I wanted to come back up with the total number of eggs, I could say margin equals 1, because that's telling R that that's what we want it to do, because again, 1 is rows. And then I give it the function. And the function, in this case, I'm dying, is sum. The name of the function is sum. And if I do that, I get the exact same thing. Okay? Two different ways to do the exact same thing. Both of them require about the same amount of typing. It's a good habit to get into using apply, because you can apply any kind of function to well, almost any kind of function that you can apply to a vector, you can apply then to a data frame using the apply function. You could also, let's say that you didn't care about each individual's total number of eggs. Let's just say you wanted the total number of eggs in the entire experiment, the total number of female eggs recovered, and the total number of male eggs recovered. You could use the exact same function, except now the margin is going to be 2, right? Because margin 1 is rows, 2 is columns. So if I do it by 2, that's the total number of female offspring we got in this experiment. This is the total number of male offspring we got in this experiment. And so it's a way that we can apply that across the this particular array. And so let's say that I wanted to recreate what my original egg data was. What I would need to do is I would need to cbind together the old egg data, and I will add to it total.eggs. Remember, that's the function that we created up here, but we could have just as easily created it here, right? Let's ignore that for now, right? Two different ways to get the same thing. Total eggs is that vector. If I want to add it to egg data, which currently right now only has male offspring, female offspring, I want total eggs added to it. I can say egg data. Again, I'm overwriting egg data. Cbind together the old egg data plus the total eggs. And now I'm back to having what I originally had. Okay. And if we wanted to, if we decided that, you know, that this is too wordy for us, maybe, I don't know why we would decide to do that, we can always change the names of the columns. And rows, but columns is the one that comes in handy. If I were to use the function called call names, and then I'm going to give it my object, which is called egg data, and then all I have to do is provide a vector that will have the new column names. So let's say I decide I want to just call it male, female, total. And now if I look at that object, now it's male, female, total. Okay? And so that is, that's how we can kind of deal with and play with these types of objects. So next, let's put, let's save this to a file so that way we can use it in the future. And I can do this. There's a number of different ways you can do this. I will do this by using a function called write.csv. And what this is going to do is it's going to write to my computer an actual text file that's comma separated values. That's what CSV stands for, comma separated values. that anybody else will be able to upload into R if they want. You could open it in Excel. You could do any kind of thing like that. And so what we can do is we can write what? We're going to write egg data. And then we have to tell R where to write it. So file equals, and I'm going to call it test write .csv. And I'm going to do that so that way my computer knows it's a CSV, and that way I know that it's a CSV. The computer actually doesn't care what the extension is. Extensions are just for our ease of interpretability, and so we're going to call it testwrite.csv. Important, before we do that, let's make sure we know exactly where we are in our working environment. So this is a really common problem that people have with R, where they save something and they have no idea where it is on their computer or why R put it on the computer. And so this all has to do with what your current working directory is, what your current location is in the computer. And so if I were to use a function called getWD in R here, it will tell me where R is currently operating. And right now R is operating at my home of home bases. It's in user, and then it's in James Fordyce. And so what do those mean? And if you understand how directories work, I apologize, skip forward 2 minutes, but this is a problem that a lot of people have. So we're all used to dealing with this very GUI interface in our computers, whether you have a Mac or whether or not you have a Windows machine, or if you use Linux, you can ignore all this, obviously. But we know that there is, we have all these various directories and stuff like that, and we can save objects to certain places. My home directory is right now defined by me, and it's because I opened up R from the basics of R. But I don't want to save things in there. What I want to do is I want to set the directory to go, I want to define the path, it's called. And defining the path is what we're always doing when we're playing around with Windows and we're clicking and dragging things into other folders. What we're really doing in that case is we are defining a new path to that file. Because as I'm sure you're probably aware, the computer doesn't physically have a bunch of file drawers with folders in them. So the easiest way to do this in RStudio is to go to under Session, and you can set working directory. And you go under Choose Directory, and now it'll allow me to define where I want it to go. So let's see, I think I want it to be in fall of 2020, I do believe, yes. So I'm going to work in there. So that is the working directory now. And this is the exact same thing that you do when you're using Microsoft Word and you say save as, and then you pick what folder you want it in. What we've done now is we've asked R very kindly to set our working directory up to be in this case, it's from my home into Dropbox, into a folder within Dropbox called Statistics Stuff Gym, and then it's in another folder within that Dropbox that is called Stats Fall 2020. So that's the hierarchical structure of where I want. And so now that I've done this, and notice that when I said set working directory, R basically wrote the code that it did. It actually used a function called setwd, and then in quotes, defining where I wanted that stuff. At some point, pointing and clicking with a pull-down window is a lot easier. But the important thing is that now I am working in the correct working directory, which means that if I write this CSV, so let's go back and look at my file right here. This is, where am I at? I'm in Stats Fall 2020, which is right here, right? It's right in there. If I were to save it, Actually, let's do this. Apologize. Choose directory. Not only, I'm going to go back to statistics stuff, Jim, fall 2020, and then, yeah, maybe I will just keep it like that. Stats 2020. I'll save it in this folder called an R tutorial. Okay, so now again, I've changed my working directory. Boy, my computer's a mess. And so now anything I save will be saved into that file. So if I go ahead and I write that, R has now written that to that file. And it was called test write, and I am in an R tutorial. And so here it is, an R tutorial. You can see here's my folder. Here's the CSV file. I could even, if I was so motivated, I could say open this, open with Excel. And now we'll go ahead and we're going to open up Excel, and it's going to pop up here in a minute. There. There's our data. Males, females, total. These are the row numbers. Okay, so that's the 10th row. These are the values. I'm easily able to open that up in Excel. And so once I have that, let's go ahead and let's remove everything. So again, I'll just hit the little sweeper button here. And yes, I want to remove everything. Okay, so now I no longer have something called egg.data. It says object egg data not found. So what I can do is I can now read the CSV. Oh, let me mention this. So when you write CSV, remember how it had those row numbers in the Excel sheet? You might not want that. I usually don't because I find it annoying. And so there's an additional argument, which is row.names equals false. I spelled false correctly. I did. Egg data. Oh, I've gotten myself into a pickle. There is no undo. Okay. And so now if I write that, it will no longer have the row numbers associated with it. So if I open back up Excel and I say open recent, I think, you can see how often I use Excel. There we have it. So now we don't have those row numbers in there. Okay, a little bit's trivia, but it does bother people when those rows are in there. Okay, let's kill Excel. Good. And now let's go ahead and empty out, remove all, yep, kill it all. Okay, so now let's pretend that we've just opened up R and we want to read that file in. So again, this is where it's important to make sure that you're in the correct working directory. If we were in the wrong working directory, let's go into the wrong working directory. I'm going to just move one step out, open, okay. And now if I were to say I want to read .csv, and what is the name of the file? So all I have to do is say it is test write.csv, and then we are going to get this error message. This is the most the only reason I went through this whole convoluted thing. This is the most common error message that people get when they start learning R. And they're like, what are you talking about? There's absolutely no way. First of all, I don't understand with I can't open a connection. What the heck does that mean? And why is there no such file? Because I saved the file and I can see it on my computer. That's because we're in the wrong working directory, right? I had redefined that I wanted to be in this directory, but I saved test write in another directory. So again, I'm going to choose my directory. In our tutorial, there's the test write. So now I'm going to open that. Now, if I read in test write, there's all the stuff, okay? So I know that that was probably 4 minutes longer than it needed to be, but it is the most common thing that frustrates the heck out of people when they start using R, is they can't find where things are. Also, you know, my data for what I'm doing right now are in that little folder, in that directory, and that would be a good place probably to put this script. It's always nice to keep the scripts with the data so that way you're never fishing around and looking for things. And so I could similarly say save as, somewhere in here I can say save as playing with R, and then I usually end those with a R, with a capital R, just so that way I know that it's an R script, and that way my computer will also know that it's an R script. And so now I have this thing in that folder called playing with R. Okay, so I'm going to go ahead and I'm going to quit RStudio for a second. And I just want to point out that if I were to open R by double clicking on that file now, so now RStudio is going to reboot. That was my doorbell. Good for me. Okay, so where were we? We had just saved test right, and we went ahead and we read test right, and there it is. But note that test right is not in our environment, right? Because R has done exactly what we've asked it to do. We've asked it to read it, but we weren't explicit that we wanted it to read it and maybe save it to an object. So I'm going to just create an object that I'll call egg.dat. Egg.dat. And now we have this object that is called egg.dat. I'm going to go ahead and just repopulate all of my stuff so that I have the original object. So this is the original object that we had, right? It was called egg.data. And then we also have this new object called egg.dat. Okay, they both have the exact same information numerically. Remember, we renamed the columns of the egg data. But what I want to point out is there's a difference between these objects. So if I look at the object, the one that we created by C binding a bunch of things together, and I said, what's the structure of that? The structure of egg data is that it's numbers. There's 1 through 10 columns, and there's 1 through 3 rows. I'm sorry, there's 1 to 10 rows and 1 to 3 columns. And then if I were to look at the structure of egg.dat, which is the thing that I just read in, notice it says that it's something different. It's no longer a matrix. It's a type of an object called a data frame. And looking at data frames, they look the same. So data frames look just like a matrix-like object, but the difference is that it's a data frame. And so data frames you can call just like you would matrices. Egg.dat, all rows, column 2 will give me all the values of the second column. When things are data frames, another way that you can extract information out of them is egg.dat and then $sign and then the name of the column. Okay, so that's giving me all the information for males, and if I wanted the females, which would be the same as 2 up here, that's another way you can extract it. And the reason why we can extract it that way is because a data frame is actually a special type of another type of an R object, which is called a list. And we're not going to directly be making lists at all, I don't think, in this class, but we will certainly be extracting information from lists. So when we start building models, and we'll call functions in R to make a statistical model for us, the object that it will create is is going to be a list of some sort, and that list will have all of the information that we might want. And so I just wanted to briefly talk about lists. The main reason why I want to talk about lists is that lists can deal with multiple different types of data. So if you recall, a vector can only be one type of data. It's either going to be numbers or it's going to be characters. It can't be a mixture of both of them. And likewise, in principle, a matrix can only be 2 dimensions and it has to be numeric. And an array can either all be characters or all be numbers. Lists can be a combination of those 2 different things. So I'm going to just create a list so we can get an idea of what's happening in a list. So I'm going to create an object called dat, and I'm going to tell R that I want it to be a list, and that's all I'm going to tell R. So right now, dat is just an empty list. And now I can populate that list. And I can populate that list by giving names to the different elements in that list. So I could say dat $males is going to get what? It's going to get egg data, all rows, column 1, I believe. Is that right? Yep. Okay. And so now if we look at dat, we can see that dat consists of one element of that list is called males. But we could further populate this. Egg dot data, all rows, column 2. If we wanted to, we could do dat $total, which is going to be egg dot data, all rows, column 3. But we can also mix it up if we wanted to, and we could have notes for ourselves. Dat $notes, and we're going to say that lists can be fun, but and dangerous, and we'll make it serious. We'll put 3 exclamation points after it. And then we could go ahead if we wanted to and just keep all of that actual data in there as a data frame. So we could say dat $, and I can call it whatever I want to. I'll call it the raw data, sure. And I'm going to say that that is equal to eggdat, which is that object that we read in. And so now if I look at dat, what do we have? We have, I didn't run all of these, did I? There we have it. And so what do I have? I have the element of that list, which is called males. And so there's the information from males. $females, that's the information from females. Here are the totals. Here's my note that I made for myself about how much fun lists can be. And then I've also included the raw data. And so if I wanted to just play with the raw data, all I would have to do is call that out. So I could create another object. Raw data gets dat $raw data. Now I've created an additional redundant object that has that. So the point is that a list can include with it a bunch of different types of data. And this is where data frames are different from matrices. And generally when you read something in using read CSV, it'll automatically convert things into a data frame because it's a more flexible kind of a format. And unlike a matrix or an array, one thing that data frames can have is they can have both characters and numbers in something that looks like a matrix, but it's not. It's a data frame. So let's say that we had our egg data, egg.data. Okay, so here's our egg data. Okay, and again we can look at the structure of that. Egg.data. Okay, it's a matrix. 1 through 10 are the rows, 1 through 3 are the columns. And let's say I wanted to put an identifier for each of these individuals that we got these broods from. Okay, so we have 10 individuals. Let's just call them A, B, C, D, so on and so forth. So I'm going to create a new vector, and I will call it ID, because it'll be the ID of whatever brood that was. And I'm going to take a little shortcut here. The shortcut is there is built-in object in R called letters. So if we were to just look at letters by themselves, you can see that it has all the letters in the alphabet. And what I'm going to ask it for is I want the ID to be the first 10 letters of the alphabet, because I know that there are 10 rows in there. Okay, so now I've created this object called ID, which are the letters. And so what I can do is I can say let's take a look at what happens if I say cbind id with egg.data. And notice that everything is in quotes here. Okay, that's not terribly satisfying because we want these to be numbers and we really want these to actually be the letters. But again, if it's a matrix or an array, it can only have one type of data in there. And in this case, it's numeric over here. But since these are letters, there's no way to convert letters into numbers directly. So it just turns everything into characters. And that's not what we want. And so what we can do is we can create a data frame. So we can say as.data.frame. Let's take a look and see what happens when we do that. And now what you'll notice is that there aren't little quote marks around this. Okay? And so I'm going to call this new dat so that way we can look at the structure of it. So now I've created this object called new dat. And let's go ahead and look at the structure of new dat. And there it is. It's telling me it's a data frame, but notice how it's saying that these are still characters. And this is why I say lists are neat, or whatever I said. They can be fun, but they can also be dangerous. So can so can data frames. Because they are lists, they can be dangerous. So if you just looked at this, you wouldn't realize that these aren't actually numbers right here. These are actually characters. And so there's a number of ways that we can fix this. One, the easiest way, which is the only way I guess we're showing, is new dat. Got something in my eye. New dat 1, I'll call it. No, let's just call it new dat because I don't want to keep that old dat. It wasn't doing what I wanted to do. I could tell R that I want it to be a data frame, data.frame. Okay. And then I'm going to give it what the names of those columns are. So the column called ID will equal that object I have called ID. Okay. If I wanted, I could say males are going to be what? Males are going to be egg.data, all rows column 1. And I'll just put one more in there. Females will equal egg.data, all rows column 2. Okay, because again, that's what our egg data looks like, right? And those are numbers. Again, we can look at the structure of that. The structure of that, it's numeric. And so if I do this, now I've created this new object called newdat, where I've given the names of the different columns, and I can look at that object called newdat. And there it is, right there. And then let's go ahead and look at the structure of newdat. And now that's where we want it. ID is indeed a character, but these are numbers. And so it can often be a dangerous thing when you're dealing with data frames, because sometimes things might appear to look like numbers, but they're actually not numbers. And so whenever you read in data for the first time into R, especially from an Excel spreadsheet, it's really important to look at the structure of your data to make sure that numbers are numbers and characters are characters. Because in Excel, it's really easy to maybe have had a period or something down at the end that nobody really ever noticed when they were looking at the spreadsheet. But then when R reads it in, if there's one character in that column, it's going to assume that that entire column is characters. And so those are our list, and that's data frame. Again, when you're reading things in from Excel or from a CSV file, generally R will get it correctly as long as you don't have too much garbage in your spreadsheet, like periods or characters where you don't want to have characters. Once you have kind of a mixed up of the types of numbers that are the types of values that are in that data frame. And that's it. And so I know that this was long and that this was slow. I'm sure for a majority of people it was incredibly too long and too slow and too boring. I promise that when we start talking about stats, things are a lot more exciting, I swear. But this was mainly for the benefit of people that kind of know R but not really know R, and then especially for people that are entirely new to R. That's the whole point of this little tutorial. So hope it was some help. And next we'll actually talk about stats. We'll talk about probability.